A normal computer is what's called binary digits. It works in terms of zeros and ones. So you can pretty much talk about anything you want to talk about, whether it's software, whether it's Windows, whether it's Paint, whether it's Microsoft. On a computer level, these work with... Hi, my name is Trito, and I'm currently doing my master's in physics. I would like to talk about the subject of matter that I'm currently studying, so that I can become subject matter expert in that. So what I'm doing currently is a master's in experimental physics. So my areas of study are superconductivity and what's called a molybdenum system. So if you go on the periodic table, you'll find that there's a certain amount of certain different elements that exist over there. So amongst those elements is one called molybdenum, that's given by the symbol Mo, and another one called rhenium, given by the symbol Re. So I sort of like study those particular elements or those particular metals, which are called transition metals. So when you dope them together, or let's say in their natural state, molybdenum is what's called a superconductor, which I'll define in a few seconds. Then rhenium on its own is also a superconductor itself. So what does that mean when we're talking about a superconductor? So quite some time ago, there was this individual who was studying certain different materials, and he studied what's called mercury, which is also another element on the periodic table. And as he was studying these particular elements, he then cooled them down. So if you think about cooling down, there's what you call the absolute scale or the temperature scale that are different. So you think of degrees Celsius, you think of degrees Fahrenheit, and then you think of Kelvin. So if you go on the Kelvin temperature, there's the lowest temperature that's probably attainable, which is close to 0 degrees Celsius or 0 degrees Kelvin or 0 Kelvin. That is in itself a type of temperature that cannot be obtained within the universe, but it is theoretically possible. So what happens is that if you cool anything down towards 0 Kelvin, it happens to be the case that the atoms within this particular element that you're dealing with, they all are no longer mobile, they are no longer moving. So the electrons are no longer orbiting around the nucleus. The nucleus itself is no longer having any vibrations whatsoever. So this is what we call a condensed state of matter. And it happens to be the case that this is theoretically possible, but in the universe it has never been observed to exist anyway. Because if you cool anything down to such a point that the electrons are no longer moving, it means that, let's say it was perhaps any solid thing that you can think of. The moment you cool it down to that low temperatures, it means that the electrons are no longer moving. So you can no longer have something which is tangible. For we cannot touch electrons, we cannot touch protons, because they're on a very small scale. So what I study is when you take any material and you cool it down almost as close as possible to 0 Kelvin, what happens is that there's a phenomenon which happens, or which was observed to happen. And this is a phenomenon where this particular material, let's say it was a conductor of electricity, it happens to be the case that as it goes as close as possible to 0 Kelvin, the electrons start to behave in such a way that they start to pair up. And when they pair up, they create what are called Cooper pairs. And when these Cooper pairs are formed, then you've got this metal is now an infinite conductor of electricity. In other words, the resistance of this particular metal, right? So you know Ohm's law, V equals to IR. There's a point where the resistance is now completely zero. It's now a material which is completely at zero resistance. So the type of materials I'm studying, they have got that phenomenon of zero resistance. So it started with mercury. Then along the years, as time went on, other materials or other elements which are conducting were found. And as time went on, it happened to be the case that the temperature you need to find or to observe this phenomenon of superconductivity also started to increase in terms of temperature. So from 0 Kelvin, or from 2 Kelvin, or 4 Kelvin, going to 6 Kelvin, 3 Kelvin, 12 Kelvin. And currently in the recent times, we now have certain types of superconductors which don't obey a certain law. So there are these individuals which are called Bardeen, Schrieffer, and Cooper. There's a theory that is named after these guys, which is called the BCS theory. So it tries to describe on a mathematical basis what happens in these materials when they are superconducting. So it happens to be the case that there are certain elements or certain compounds that if I say I take molybdenum and I join it with a different element, now I've got what's called an alloy or a compound. Right? And it's an alloy when it's different metals that are joined together. So there are certain alloys which were then discovered to be superconducting, but their behavior can no longer be described within this normal type of theory called the BCS theory. So they are then called unconventional superconductors. And amongst these, we've had the recent discoveries, which are very good conductors at almost close to like hundreds or 200 Kelvin. That's almost as close as possible as we are to getting to room temperature. By what is this? Why is this important? Why is this important to any everyday individual out there? So currently we have got new developments in computer sciences or in computers, some type of computers which are called quantum computers. Now, a normal computer is what's called binary digits. It works in terms of zeros and ones. So you can pretty much talk about anything you want to talk about, whether it's software, whether it's Windows, whether it's Paint, whether it's Microsoft. On a computer level, these work within what's called binary digits. But when you're talking about quantum computers, you are no longer talking about ones and zeros. You're talking about ones, zeros, and something else in between. So when you're talking about a normal computer, you've got a 1 which can indicate, for example, an on, and a 0 which can indicate an off. So you've got lights, communication, which are talking about the science. So a certain combinations of ones and zeros give a certain message. So any letter on the alphabet could be a set of, let's say, ones and zeros that give you the letter A. For letter B, you've got ones and zeros that are combined to give you the letter B. But now, if you're talking about quantum computing, you can talk about certain numbers which don't necessarily have that definite 1 and 0. They are anything in between. And these help to say that you can pretty much do a normal computation that would take you, let's say, 1 billion years on a normal computer to calculate. Let's say it's a number that you want to add together. But for this number on a normal computer, it takes you 1 billion years. With a quantum computer, it's something you can do within minutes. So this means computational power increases drastically from what is currently available to us as human beings. And these things have been developed currently, these quantum computers, in different regions of the world, particularly in Europe. But the problem is, for you to have a quantum computer, you need a big room. And this big room needs to be refrigerated at like very low temperatures. So it's not something that you can say you can have in your own room, your own quantum computer. But you can only have it at particular facilities. Now imagine if we can create a superconductor which is now at room temperature, because for these quantum computers to work, they need superconductors, which are zero resistance materials. And for you to have those zero resistance materials, you must be at certain low temperatures. Now to imagine if you can now have those materials at room temperatures, which means that you can now have quantum computers without needing a fridge. And if that's the case, it means that we can now do many computations without needing to go at zero or those lower temperatures. That means in your house, you can have a quantum computer. And if that's the case, if it's AI we're talking about, you can develop an AI so powerful that 300 or 3,000, or how many number of human beings you can think of that can think, right? They would not necessarily be able to compete with this type of computer, which would mean that technology itself, as we know it, would drastically change. Would be living in pretty much the sci-fi universes you see on the televisions. So that's practically what I'm studying. I'm studying it, of course, at those conventional levels, but I'd like at some point to increase the temperatures to find a room temperature superconductor. So I would say that that is currently my area of expertise, or my area of studies rather. And the goal is, if at all possible, to either develop a theoretical framework which can allow us to find room temperature conductors, superconductors, or to do experiments that will allow us to get to a point where we have room temperature superconductors, or in the very least just to understand how superconductors work all in all. So that's what I'm currently doing, and yeah, it's very, very interesting. I think that's all that I have to say.